Quantum Foam, Episode 28. The Standard Model.
Physics. Physics is at the foundation of all the mathematical principles that guide the heavens. You have to understand physics.
More than likely that's not going to happen, but
Forces which govern the universe. Physics.
we finally have the information we need to read what we need. That is what is going on. All right, we're getting some other content here. It seems to me somebody else is getting called. Particle physics. This has been rightly named the particle zoo for a good reason. It's really hard to understand. Michio Kaku says he got his PhD for learning 1,000 particles. It's because of all these virtual particles and other such things that it is crazy, and why we call it a zoo. It's a model, it's not complete, and things within the model have been changed over the decades, not surprisingly. So we are going to attempt to, not surprisingly, understand all these particles. 17 particles, 12 fermions, 5 bosons. So originally we had thought that everything was made of only 3 particles. As it turns out, there were indications that other stuff was going on. The whole purpose of what this standard model is trying to do is describe forces and matter in terms of mathematics in order to learn where we came from, what will happen in the future, what's happening now, why things are doing what they are, etc.
That is why we are here.
We should really get back to trying to figure out how to present this theory of everything, or people are just going to think that it is all hogwash and that some asshole made it up just to piss people off. Obviously that is not the case. That's bullshit.
All right, go on.
The deepest and most clear-cut requested questions.
We simply need to hear more on this standard model of elementary particle physics.
So the standard model, carrying forces back and forth. You've all heard of the LHC, Large Hadron Collider. Hadrons are bigger particles, protons, smashing around protons. It's fundamental what they're doing there. But fundamental does not mean fundamental. Fundamental just means the beginning. Fundamental.
One more thing about that. Okay, so fundamental forces, gravity, and the electrostrong and the electroweak forces are what give rise to all other forces and phenomena that we observe in the universe around us. That is all he means by fundamental. This topic is going to be a little harder, but we are here to help.
So we've all heard it. The Higgs Boson. The Higgs Field. The Higgs Field behaves with wave-particle duality. Quarks and antiquarks are paired up out there. Cosmic rays and such. They make up mesons. It gets much more complicated than that, and we will touch upon that in a bit. So the easiest way to take a stab at this is to look at your 2 charts of electron, muon, tau, and up charm, top, down, strange, bottom quarks. And the leptons have their ghosts too. And then also the Z boson, W boson, the photon, and the gluon boson.
The gluon boson has a spin of 1.
Scalar boson, Higgs boson, and then gravity. So all of this is everything. What? How is that everything that's on one page? I see 16 things. How is that everything that's on one page? My middle finger is to the sky right now. How is that everything that's on one page? No, hold on. My middle finger is in your face. Why am I holding my middle finger up to you? My middle finger is in your face. Both of them? I even have both with the pinky flip too. You're crazy. You're crazy. We can get into chirality. You're crazy. And other stuff later. I have to get back to what I'm doing now.
Very theatrical.
So we go into this particle physics list. So these are all of the things that over the years they have put together in a rubric and a chart for before you do an experiment, after you do an experiment, where you put your answers. So it's like you make up a form, you make up a rubric to run it, and then fill the rubric with the information from the experiments, and then you analyze the differences between the predictions and the associations you made then and now. This is repeated over and over again by multiple parties until somebody figures out the next step that another person did not see, and they figure out a little bit more. But there is definitely a back and forth on the front lines. Is this true or not? Maybe not. Unfortunately, if I had the whole story, I could just be like, all right, here you go. Click here, download here, insert here, export here, occidental here, inflection point here.
While you are making space-time points that have mathematics beyond normal 3-space.
So we have to figure out what this stuff means. We are trying to describe forces here. Strong, electromagnetic, weak. So we are trying to figure out how to use this model to do more physics. That is the point here. We're taking a look at all these different particles and where they come out of, what laboratory they come out of. They are figuring stuff out of Fermilab and SLAC. They are figuring stuff out of CERN. And then there's others. Neutron colliders, where they can study particles that smash at certain energies, certain densities, certain amounts of certain stuff. They look at particular particles. I am interested in a particular particle that only lives like a femtosecond, and it doesn't even exist in our normal space-time. Now, you tell me how a random person to another random person, how does knowing that little itsy-bitsy piece of knowledge help either one of these individuals? Two people that are trying to interact in some way. They are talking, they are speaking, they are in the same room. That is a very good question, because that is about how far the lengths go. So it's really all about this wave interference. Electrons are left-handed. Special relativity actually agrees with a lot of this stuff in the standard model, but gravity has problems.
Implausible, since this area of physics covers the so-called fundamental forces. This automatically implies it is supposed to cover it all and explain everything. This, we know, is not the case. It is as though the school of thought which created the standard model only read my papers from 1905 on special relativity, which included only space-time as a fabric, and light and potentially mass as waves through this fabric. Remember, I added acceleration and gravity in 1915, and they proved it after the First World War. During an eclipse, the standard model says little about quantum gravitational mechanics as it applies to the four fundamental forces and the Higgs field, the so-called fifth fundamental force, which is given and understood in the form of tensor field mathematics. How does this fit together with our current models?
How does that fit in? That's what we're looking at.
Yes.
That is something that needs to be clarified. I've seen that around.
I'm sure you have.
So these guys, this solution was formulated by Higgs, Englert, and Robert Brout. They proposed that the space is filled with a field, this Higgs field. It interacts with the weak nuclear force in particles to give them mass. This happens because even though empty space is empty, there's still a Higgs field there that is non-zero. So this is where it violates the symmetry. That's where that comes from. So this is why we don't know if symmetry is the way it is or asymmetry is the way it is, which that refers to this non-zero ground states. If they have energy, they violate the symmetry, and so they are asymmetric. We've seen both. So different theories have been tossed around about what can give particles mass. This is the one that is now mostly accepted as true, so I don't know.
We will cover more on the Higgs field later on down the line.
The Higgs field does exist, so this is all very important research. That is all I'm going to say about it right now.
They always seem to leave my general theory of gravity out when dealing with mathematics concerning particle interactions under the standard model.
Essentially, they don't even attempt to describe gravity because There's no sense that anybody has made out of any interactions that they have seen and or calculated that would make them think so.
The problem is that on those scales, we simply cannot really detect any noticeable gravitational effect other than what we can figure using the equations of the Standard Model.
There's only so much stuff you can do with only so much. That's why it's quite a weird concept, because it has two multiversal components to it, making it sort of just a double whammy, because it looks at things again twice, even as it exists. In a way, it's like you could sit here all day with these exotic hadrons. Oh, I'm cool. I'm smashing a little tiny particle together. I'm actually trying to compare a theoretical particle that I'm throwing at you with enough kinetic energy to change the momentum of a mosquito. What? You're comparing little tiny pieces of dust and bugs and organisms with something on a scale so much smaller than anything that most people see ever. There's Higgs bosons, Higgs fields, dualities. There are quark-antiquark pairs. Those are called mesons. We were talking about those.
Mesons are unstable subatomic particles composed of an antiquark and a quark. The mesons interact with both the strong and weak nuclear forces. Mesons have integer spin. They don't obey the Pauli exclusion principle. Mesons are all over the place. They are present during nuclear interactions and can have properties like total angular momentum, parity, C parity, G parity, etc.
Baryons are your normal stuff. 3 quark configurations. 2 ups and down, 2 downs and an up, 2 bottoms and up, that kind of thing. Just a designation. Each thing has 1/3, 1/3, 1/3 spin. It works out. Is Q affected by G? And what I'm putting down as certain mathematical loops that for one reason or another take longer than most to wrap around and amalgamate into a container of force-carrying particles, amalgamate bosons, fermions, amalgamate all these little tiny particles that are few and far between from one another, like to go down in quantum state. Instead of a different realization, it's probably more like a valley, a bunching of bosons, Bose-Einstein condensates. We get into what each of these things are.
Bose-Einstein condensates.
Okay, so you have your first generation, second generation, and third generation of quarks and leptons. So a proton is made of 1 down and 2 up quarks. A neutron is made of 2 down quarks and 1 up quark. And that is the easiest example of how there is 3 particles that make 1 particle that is a proton. That is how atom smashing works. In a way, you can look at the inverse, opposite, and forward-moving time direction light mass wave picture that you see. That is what we see. That is the same thing as a point. What's the counterpart? Think about these questions philosophically, mathematically, and physically. What is the opposite of a singularity? What?
That is deep. You got me a little more interested now. This is like back when you took astronomy in college for the first time. At the end of the class it was like 1 divided by time equals quantum foam and infinity. Something like that. What the hell is 1 over time? What is the opposite of a singularity?
What is the opposite of a singularity? Does it have 2 charges or 1?
It depends on your model and notation.
Is it a constituent? That is what's happening here. Splitting constituents, splitting atoms, emitting energy, consuming energy, creating energy, not creating it from nothing, converting it. A certain process creates energy, but that's only in reference to that certain process. Generally speaking, you don't just create energy. It is impossible according to Einstein. Conservation of energy. There's not any more or less energy in the universe than there already is.
Very true, but we are approaching the level of mathematics where it becomes indistinguishable between computer simulations and reality. The same mathematics required to communicate at faster than light speeds and distances. Networks have to modulate and demodulate the binary communication. This is what drives the digital information. A modem is inside our devices and transmits, receives, and otherwise relays communications from point to point. We are attempting to communicate with devices that have traveled relativistic distances away from Earth. There is a lag of about 1/3 of a second between the surface of the Earth and some geosynchronous orbits.
Hold on, Einstein, I know you're on a roll, but we gotta take a break.
That's quite alright, good sir. This topic is definitely a doozy.
Obviously, this is the midpoint of episode 28, the standard model of quantum foam. Quantum foam.
Also, for comparison, there is about a 20-minute time lag between the Earth and Mars. It varies heavily based on the position of those two planets around the Sun. Let's get going. Calling all scientists, researchers, technicians, assistants, everyone who works in science. Develop now. Build the future. Start projects now. Get your kids involved.
I got it from here, Stephen.
Alright, I have some place to be, see ya.
Go ahead and finish, Mr. Einstein.
Thanks, Sir Newton. Always the gentleman. If the human race does not forge science forward, we will never explore the final frontier. So the amount of energy in the universe now is still the same amount present at the creation.
It's not going to increase or decrease. So the amount of electricity that is here is here. It is almost as though electricity is the blood of 4D hyperspace, the blood of 4D beings. And that is a very peculiar thing to think about. So we get into more of these particles. Your electron, negative charge, your muon, your tau, then your electron neutrino, your muon neutrino, your tau neutrino. Those are the ghosts.
It is almost as though electricity is the blood of 4D hyperspace.
The electron, muon, and tau. Normally it's just the electron, right? But there are other instances where these other ones appear, theoretically, in your field of view. There's a difference between where you're looking, if you're looking, and if you looked or did you look. Those all have distinct meanings. 12 particles of matter using 3 forces. Did you look? And it's caused by 4 particles. It's caused by the exchange of 4 particles. Proton is a large hadron. Come on, look at these s orbitals. You can see it. So you can see it. These are used to explain all the other particles. You can see it. All these other quarks. So we got the quarks. You can see it. You can see it. Up quark, down quark, charm quark, strange quark, top quark, bottom quark. You can see it. Proton, 1 down, 2 up quarks. Down negative 1/3, up positive 2/3. That is the difference between them. There are certain aspects of each of these forces. That is the point of what we are trying to take away from all of this. The point is these describe beautifully 3 of the 4 forces, but they have trouble describing gravity. Let's go into what they can describe so we can get that out on the table. I mean, it depends on where you're at in your rural temporal vacuum. So to help understand this a little bit and what the difference is between some of these, fermions are matter particles. Those are the ones that deal with particles that have matter and whatnot, electrons and such. Fermilab Enrico. That's where it comes from. Understanding nuclear physics. This is nuclear physics. It's just the word nuclear is associated with a nuclear warhead. That's all anybody ever thinks about when you say nuclear. But remember, there's something called a nucleus, the center of the cell, right? The center of the animal cell or the plant cell. And that's why they call them nuclear reactors. We have a nuclear reactor. But that is the weak force interacting. So the weak interaction, there are issues with this. So it is experiencing different things like charge parity violations.
Parity is a son of a bitch to understand sometimes.
You are right. Explain a little more about the conjugation parity concept.
Sure, the C parity or charge parity is a multiplicative quantum number of some particles that describes their behavior under the symmetry operation of charge conjugation.
Indeed. It also has to do with the very peculiar phenomena we observe that demonstrates this symmetry spontaneously breaking down in unexpected and so far unexplained ways. Very exciting.
During this conjugation, the various quantum numbers change or are assigned, electrical charge, the state of the quark system, etc.
Fermions follow Fermi-Dirac statistics. We are breaking down these particles. So what is the particle content? You got your elementary particles, elementary fermions, elementary bosons, half-integer spin, integer spin, Fermi-Dirac statistics, Bose-Einstein statistics, and there's various things about each. The quarks all have color charge, and that's a charge according to a color, according to something that we can describe with a color, which is why we went over chromaticity back in the day. Now, a couple episodes ago.
Chromaticity was episode 11, the first one of the last decimal of the podcast.
You need to understand that colors are just a way to describe stuff. Understanding the gradients and stuff like that, things that we are interested in. So it can go quarks and antiquarks, half spin. They participate in strong interactions. Up quark, down quark, charm quark, strange quark, top quark, bottom quark. 3 generations. Electron Neutrino, Muon Neutrino, Tau Neutrino. Those are leptons and anti-leptons. Spin of 1/2. No color change on the charge as it appears. Anti-leptons compared to the other one. So we just assimilate that in. We assume that for all the rest. We can describe it in a way like that. So there are 4 fundamental interactions. Photons. W and Z bosons. W plus, W minus. What we're really trying to do here is go into detail briefly and then come back out so that we don't get bogged down by all this crazy information that doesn't quite make any sense, but the mechanism of interaction between subatomic particles is responsible for the radioactive decay of atoms. So this is very important for reactors, obviously. So we got the boson side, elementary bosons. These have integer spin, a spin of 1, a spin of 0. They carry force, 4 kinds. The photon, the electromagnetic interaction, lambda. We're talking about magnetic fields and the like. Electromagnetism. What we're more specifically worried about is this weak nuclear force and this weak interaction with this decay stuff. How does this stuff actually do this? How is it that this force randomly is a force? Its purpose is to decay. It just changes. How many protons do you got? And so it gets pretty complicated. The electromagnetic interaction. They're the intermediate vector mathematics that describes the bosons.
The intermediate vector mathematics.
That's what they are. They mediate the weak interaction. So there are 8 types of gluons. It holds them together. This particle acts as the exchange for the strong force for quarks.
It's also neat that the top quark was only discovered in 1995, but to make sure that astrology, mysticism, and so-called paranormal activities don't attempt to replace already well-understood areas of math and science, we have to pay attention to detail.
Gluons, that is what glues them together, hence their name. These 4 fundamental forces. So you can also call these bosons gauge bosons, of course. They're the force carriers. They mediate this mysterious force. So we just need to understand what most of the main ideas are and what the main particles are out of here. How can you know everything if you don't even know particle physics? Well, you can't, but you never really know anything, everything.
Well, you can't.
So does what you're doing obey Bose-Einstein statistics, or does it obey Fermi-Dirac statistics? Particle physics. Let's make some statistics that encompasses all of that. That is what I'm doing. I am trying to formulate a new platform to formulate more theories so that we can describe what we need to and get the answers that we request. So to actually crack the theory of everything, you really need to actually build a quantum computer that can theoretically build anything, anytime, any place, anything, any particle, programming the universe type stuff. That is a questionable topic, to say the least.
You know we love those kinds of topics, though.
So there's mesons, pions. What's a meson? Quark, antiquark pairs. These are jumblings of particles that are found in certain locations during certain tests, times, and situations. I'm just talking about this colloquially. They've been seeing these in atom smashers since the 60s. There's the annihilation between antimatter and matter. The different flavors of quarks can be colored. Red, green, blue quarks. And anti-red, anti-green, anti-blue quarks. So you can have anti-red quarks and blue quarks and other combinations that don't make any sense. But the fact is, that's what I'm saying. This entire model has been written by these guys who did this stuff, and it may not even mean anything. That is the problem. It is not to downgrade the monumental academic work that has been done to get to the point where people know what they know. It actually is a lot of stuff. There's a point where one's head hurts. It may not even mean anything. You got to figure that one out. We can go deeper or not, but I say not at the moment. You got the runaround of the basic concepts. We have dabbled into some of the specifics. The electromagnetic and strong force don't generally care about handedness, but the weak does. Charge parity invariance.
I have more on that as well. While the strong and electromagnetic interactions obey charge conjugation symmetry, the weak interaction does not. As an example, neutrinos are found to have left-handed parity, since charge conjugation would leave the spatial coordinates untouched. Then if you operated on a neutrino with the C operator, you would produce a left-handed antineutrino. But there is no experimental evidence for such a particle. All antineutrinos appear to be right-handed. The combination of the parity operation P and the charge conjugation operation C on a neutrino do, in fact, produce a right-handed antineutrino, in accordance with observation. So it appears that while beta decay does not obey parity or charge conjugation symmetry separately, it is invariant under the combination CP.
Parity inversion. Some of them obey the Pauli exclusion principle and some of them do not. In the case of electrons in atoms, it is impossible for two electrons to have the same values of the four quantum numbers. Electrons must have opposite half-integer spin projections of 1/2 and negative 1/2. It's just such a weird thing. What does that mean? I don't get it. What? The fuck mean? I don't know. I don't know. What does it mean? I don't know. What is a particle? Too rigorous. Rigorous.
It can't possibly be that hard.
The main thing that you got to get out of all this is that it's kind of weird, but the Higgs boson is the only known scalar boson. I'm digging into the random issues they have with these models. I'm looking to supersede their understandings of these because it may not be understood correctly. It may be too new of an understanding to have been shuffled and not have been updated yet. That's why the audio is way faster than any kind of written anything. So that's why I'm doing this. I am reaching upon an imaginaryism, an imaginary object. You have your direct object, you have your indirect object, and you have your imaginary object. An imaginaryism.
An
Imaginaryism. Your imaginary object is what I'm talking about. So you got fermions, bosons, up, down, charm, strange, top, bottom, electron, muon, tau. Then electron, neutrino, muon, neutrino, tau, neutrino. Then you got the bosons. There's gluons that hold everything together. Photons that get spit out when things happen. Neutrino, There's W and Z bosons. There's Higgs bosons. All of these things interact with various things. We found different interactions emit different particles. This interaction emits this particle. This interaction emits this particle. It's old news. In quantum chromodynamics, such things happen. Even massless particles are given a mass. It's called a rest mass as part of the system. Your standard model. This is my standard model of my image of what I think their model is trying to tell us.
Awesome job. It's about time to finish it up.
This is it for episode 28, the standard model of quantum foam.
The zeroth wave disclaimer.
The views and opinions expressed in this podcast are those of the author or authors and do not necessarily reflect the particular views, thoughts, or opinions of Zeroth Wave Productions, any of its sister companies, its parent company, Zeroth Enterprises, or any other entity which had existed, will exist, or which, quote-unquote, presently must exist outside the realm of our current space-time.
Quantum Foam is produced by Zeroth Wave Productions.